Can you first check the audio? Check, check. Yep. Can you put that on for you? Yes, please. Thank you. Batteries are a little low. Okay, thank you very much. All right, everybody. The usual stuff, please shut your laptops and get your name tags out, and here is my TA. Get on Zoom. One. All right, let's begin. This is the last of our series of lectures on training neural networks. So here's what we've seen so far. We train a network by minimizing a loss function. A loss is a function of the network parameters, which computes the average divergence over a bunch of training samples. The specific set of training samples may change from step to step. We also saw that this loss is not really the function we want to minimize. What we really want to minimize is the expected divergence. Kishore, you still don't have your name tag out. Okay. So, and we minimize this through gradient descent, where we take iterative steps against the gradient. Now, we also saw that in principle, if you want to optimize the network parameters to update it, to adjust it everywhere over all of the training samples at each step. But this can be slow, and so we use incremental update algorithms like stochastic gradient descent and mini batch update to speed it up by updating the parameters using random samples chosen from our training set. These are faster to converge, but have greater variance from step to step, and so may end up result in worse solutions. And we also saw that trend algorithms smooth out variations in the incremental update methods by considering long-term trends in both the gradient and the variance of the gradient itself, or the squared magnitude of the gradient itself. So we're going to look at a few more topics to close out this business of training. We're going to look at divergences, normalizations, dropout, and a few other tricks. First, the divergence. Now, here is the loss. The loss is the average divergence over a bunch of training samples. And how well your network converges to its optimum is going to depend very seriously on the nature of the loss function itself. We saw earlier during this course that some kinds of error functions were really not very useful. Anybody remember an example? Step. The step. Am I correct or am I not? you cannot differentiate it. I mean, you could, but the derivatives are either going to be 0 or infinite, and they're not going to be useful in telling you which way to adjust your parameters. So the choice of loss function is going to have a great impact on how well your network trains. Ideally, the loss function must have a shape that results in a significant gradient in the direction of the optimum and not in other directions. You want it to guide the algorithm to the solution. So you can have loss functions of this kind, something like a loss function like the one to the extreme left. The jagged nature of the loss function means that you're really not going to do a very good job of optimizing your network. Those are the kinds of loss functions you do not really need. The one in the middle, it has a nice gentle slope towards the optimum, and then this slope speeds up right near the optimum. Would you call this a good loss function or a bad one? Bad. Why is it bad?
It can overshoot and miss the minimum.
So, and what about the one to the extreme right? That's a good one. So this is the kind of behavior you want. If you have both of these are smooth, they're continuous, they lead to the loss, they have a global minimum. But in the first one, out far away from the minimum, the slope is very shallow. You're going to take lots and lots and lots of steps to get to the vicinity of the minimum. But once you get there, the slope is so steep that you're going to bounce around and probably jump out of the minimum. On the other hand, the one to the right has this nice bowl shape where when you're far away, the slope is large. You're going to take large steps. And then as you approach the minimum, it begins to get shallower. And so your steps become more careful. So this is ideally, you want a quadratic shape for this function. If it's more than quadratic, then it becomes too flat near the minimum. So these are the kinds of loss functions we need. And we saw that our primary loss functions are one of two. The L2 loss, which is basically just the quadratic error between the output of the network and the desired output of the network. This is what we used when we were trying to predict real valued outputs, where the real values were not probabilities. But if you were performing classification, then what we wanted to output were probabilities. And in that case, we use the KL divergence. Now, why would we use the L2 loss, KL divergence, and not the L2 loss? Now, I've just explained the nature of the loss function that I would like to see. And here's something. If I look at x squared, this has a bowl shape. And, we like this. What about x raised to 4? What would it look like? X raised to 4 is going to look like this. Right? X raised to 8 is going to look steeper still. X raised to infinity is just going to give you vertical walls and a flat bottom. So in this case, is x raised to 4 better or worse than x squared?
Worse.
Worse. Why?
Because it's steeper.
It's steep. Steep is good when it's far away. The problem is when you begin to approach the minimum, it becomes so flat that the updates are going to be too small. And so you don't like functions of this kind. Now, let's look at these two loss functions, the L2 loss and the KL divergence. The one to the left, the one on top is your KL divergence. When I'm trying to predict probabilities, that's the one we said we would use. The one at the bottom is your L2 loss. Which of them seems to have the nicer shape based on what I just told you?
Yeah.
It has the nicer shape?
L2.
L2 seems to have the nicer shape, right? The KL has this horrible flat structure right near the optimum. So if, for example, if my desired output value is 0.5, my target output value is 0.5, as I go away from 0.5, the divergence just blows up, and it's infinitely bad, right? Whereas the L2 loss has a nice bowl shape. So why do we use the KL as opposed to the L2 when we are performing classification? Anybody want to hazard a guess? You probably don't know the answer, but yes.
So this is.
Pardon me? Yeah, sure.
Like that's usually where it is.
It doesn't matter. It's still going to be. It's going to have the structure. So here's the thing. When you perform classification, you start off with the initial portion of the network, which computes some kind of a vector. The penultimate layer of the network computes some value y. Then you have an affine transform which computes the value z, and the z goes through the softmax, and this is the predicted value. This is, right? And this y is the predicted probability output by the network. So what we are looking at over here is the divergence between the desired output and the actual output of the network. That looks like the bowl to the left. And so if this divergence, if I use KL, I get this flat bottom shape. If I use the L2 divergence, I get the bowl. But that is a function of this divergence with respect to this guy, right? What about the function of the divergence with respect to Z? It turns out that this has a surprising shape. If I look at that, when I look at KL as a function of Z, then it has a beautiful bowl shape. Whereas if I look at the L2 loss as a function of Z, it begins to look like the flower. Now tell me which one is the better divergence? Yeah, clearly, right? So it's impossible to look at local characteristics to determine how the overall characteristics are downstream. And in the case of classification networks, clearly, KL is the better divergence to choose. And in fact, so here it is for 2 dimensions. Again, the figure to the left shows you this nice flower-shaped loss function as a function of the affine value Z. If you were to use the L2 divergence between the output of the network and the desired output. Whereas this figure to the right shows you the function divergence is a function of Z when you're using KL divergence, and this looks like a bowl. So which is why when we perform classification, we have the ability to use the KL divergence, and that is indeed what we will use.
Professor, why don't we use KL for regression as well?
This only happens over here because the outputs are constrained to sum to 1. If you did not have that, this behavior goes away. Right?
Got it.
So you have the equivalent of a KL divergence for terms that don't sum to 1. It's I forget the name. It's a Bregman divergence of some kind, and it will have a similar shape, but then it's not so nice. So, L2 is not convex, while KL is convex when you look at it as a function of the affine terms. Now, we also saw this, both in your quiz, I think, and in the previous class, that regardless of whether you're using L2 or KL, because the output activation for L2 is just the identity transform, whereas for the KL, the output activation is the softmax or the sigmoid. So we found that the derivative of the divergence with respect to the affine term Z was always the error, which is why historically backpropagation has been called error backpropagation, because what is being backpropagated once you get to Z is the error. Okay. I think everybody would have answered both. Can someone on Zoom answer the first question? Someone on Zoom?
Would it be KL?
KL
Yes.
divergence.
Because as far as the affine term Z is concerned, it's symmetric with respect to the way, it's just the product of the weights and the output of the previous layer. So it's symmetric with respect to the weights and the output of the previous layer. Z is just W times something, right? And so the behavior of the loss function with respect to Z is going to be the same as the behavior of the loss function with respect to the weights. It's also the same as the behavior of the loss function with respect to the output of the previous layer. So if this guy is convex with respect to Z, it's going to be convex with respect to W. It's also going to be convex with respect to the output of the previous layer. And so KL is it, right? Whereas L2 is not. Now, this only works when you have a softmax output layer. What about the second question? Does someone here want to answer it?
The error y minus d.
So for the most popular networks, the gradient with respect to the final affine value Z is y minus d, right? You saw this in the quiz. Okay, let me move on. Any questions? Yeah.
Can you show one more time why, if we know that we're convex, like the derivative with respect to Z, that we're convex on the derivative with respect to W?
Okay, because Z is W times Y.
Z is W times the layer before.
Yeah, no. Z, sorry, Yn minus 1. So Z is Wn times Yn minus 1, correct?
Yeah.
So if it's convex with respect to Z, it's just a linear transform. It's like a rotation of the space.
Is convexity preserved in a linear transform?
In a rotation, right? When I'm doing Wy, what is it? That's just a rotation. So if I have a convex function on a sheet of paper, and if I rotate the paper, does it stop being a ball? Like,
Because of the definition, if you flip it upside down, now your lines are going to be underneath it, right?
not the whole point is this. What kind of transform is this one? What kind of transform is this one?
Linear.
Yeah, it's a rotation of the space or a scaling. So think of a bowl on top of a piece of paper, right? And here's one, right? So if I have a bowl suspended on top of this, if I rotate the space, will the bowl stop being a bowl? That's about it. So any linear transforms are just rotations, translations, and stretching. It's not going to change the shape of the bowl. Okay.
Okay.
It's nonlinear stuff that makes things bad. Okay. Did that answer your question?
Yeah.
Kind of, okay.
Yeah.
Put it on Piazza, I will answer it. Yeah. It's easy to show.
Thank you.
All right. So what we did see is that gradient descent can be sped up by incremental updates and improved using smooth updates. We saw this in the last class. Our latest addition to this story is that the choice of divergence affects convergence. It also so it affects the learned network and whatever you can get from it. Here's another important thing. We're working with mini batches. We saw that mini batches are the way to go. What is the basic assumption when we worked with mini batches? Anybody? We are performing random sampling. When you take random samples, what is the underlying assumption?
That they're representative of the greater.
That each sample is representative of the greater collection of data. So you expect that statistically every mini batch looks like every other mini batch. So if you were to plot a scatter in say 2 dimensions, and if each of those patches represents a mini batch, you'd expect that all of them sit in more or less the same location. What will happen is that they're going to be different. So now each mini batch has a shift with respect to every other mini batch, and you cannot say what the shift is. And this shift can be very large. So when you have something of this kind, optimizing on one mini batch really does not tell you anything about what's going to happen to the function at large over the entire space. So what we like to do is to kind of normalize the mini batches somehow. Use the local statistical characteristics of the mini batch to move it to a location where things have a more global character. So we'd like to move every one of these mini batches back to where they should have been, more or less, had they actually been truly representative. And we don't know where they must be, and we don't know where they currently are. So both of these must be determined. And remember, this can happen at every location because a neural network is a hugely nonlinear function. If I start off with 2 points which are this close at the input, 4 layers down the network, they can be this far apart. And we can start off with 2 points which are this far apart at the input, and 4 layers down, they can be very close. And so fixing things at one position doesn't mean that they stay fixed through the network. The relationships stay fixed through the network. In any case, we are left with this problem. We want to drag all of the mini batches to some location where we think they now begin to be more representative of the overall data. Now, since we don't know where they currently are, and since we don't know where that location is, we must estimate it, and we do it in a two-step process. Since you don't know where the mini batch currently is, you do know that each of them can be dragged. So, if we did this naively, we'd have to determine each of those 4 yellow arrows. That's not a very reasonable thing to be doing because each mini batch has a different arrow, right? So we are going to move every mini batch down to so that they are centered at origin and have a unit variance in every direction. So this is something that you can do because the statistics that must be derived to move points to origin can be derived from the mini batch itself. They're just the mean and the variance of the mini batch. Once things are there, then you have to determine one little shift which moves anything that's at origin to the location that it must be. And so this is how we're going to do this normalization to deal with the variations, the fluctuations from mini batch to mini batch. This is what we call batch normalization. So that makes sense to everybody?
Why do you have to move from 0 to origin?
So we're assuming that there is some statistical distribution. It's not that everything is centered at 0. And this particular set of values at that layer in that neuron lives somewhere. We must find this place and move it there. Right? So okay, this one was easy. Can someone on Zoom tell me the answer to this?
Mini batch.
Could you repeat that, please?
Mini batches.
Yes, indeed, right? So batch norm accounts for the covariate shift between mini batches. Now,
Question, sir.
yeah.
So please, does it suffice to say that for given when taking mini batches in a data set, you said you just have to ensure that each of the mini batches have the same distribution.
Yeah.
I think this would work if assuming they all have the same normal distribution, then the resulting will be the same. But is it possible that even though they have the same distribution, the sum of the entire data set has a different distribution? So what I'm trying to say is, like, do we ensure that each of the mini batches mimics the
That's what we would like to do. So we would like to have each of the mini batches mimic the global distribution. So that is the hypothesis that we began with when we began speaking of mini batches. The reality is that it's a sampling process. No matter what you do, the mini batches are going to have minor differences. But then the reality also is that neural networks are hugely nonlinear things. So they can magnify small differences into huge differences. And also, conversely, shrink huge differences into really small differences. So while your mini batches might look very similar going in, say a few layers down the network, you might find yourself in the situation that you just saw on the board in the pictures. And then you have to adjust them all over again. Did that answer your question?
So thank you.
Yeah, so yeah.
Are there empirical studies on when that kind of thing happens, where like small differences in your batch?
It's very easy to actually come up with examples where that happens, right? So I can take, for example, a ReLU. If I'm sampling data, something that's slightly to the right is always just going to, with a steep slope. Anything to the right of 0 is going to become get moved way out towards the boundary. Anything to the left just gets squished to 0. Right? It's easy to see. You can come up with examples. It's very easy. And because our activation functions are nonlinear, this happens all the time. So again, batch normalization is a shift adjustment that happens that can happen at any location. But typically, here's where we apply batch norm. We apply it to the affine value that goes into the activations. But there's some argument as to whether it must be applied there or whether it must be applied after the activation. There are different variants to this. But the concept remains the same. And the concept is this. You're going to work on mini batches. So now each one of so here's what the individual neuron looks like. You have a bunch of inputs coming in. You compute an affine value, which is a weighted sum plus a bias. And now what we are going to do is that instead of just directly applying the activation to this affine value z, we are going to be adjusting this affine value z before you apply the activation. And this is the batch normalization step. So over here, the first thing we do is to compute the mean. Remember what we did here in this picture? We first moved everything towards center. How do you move everything towards center? You compute the mean of the batch and subtract it from every instance. And now the global mean is 0. But then that's not enough. You also want to standardize the variance because different mini batches might have different spreads. And so how would you do that? How would you standardize the variance? Anybody? Divide by the standard deviation, right? So this is what we do. The very first step is you compute the mean of the mini batch, the collection of instances. I'm not speaking of the components of the vectors. I have a collection of vectors. So I'm going to compute the mean of the collection of vectors. I'm also going to compute the component-wise standard deviation of the collection of vectors. It's better to think of this component by component. So if you can, because if I drew this as a network, then here is what it would look like. I have a bunch of neurons from the previous layer, n-1, and at each neuron, I get a value z. I'm going to get this scalar z for every training instance. So now it's a collection of scalars. It's convenient to think of it that way, right? So that's what we've got. This is the mean of the set of scalars. Then you compute the standard deviation. I subtract the mean, and then I divide by the standard deviation. Now my collection of data is 0 mean unit variance, right? But then I have to move the entire thing to a new location. And so I have started off with everything that's 0 mean and unit variance. If I want to move it to some new location out here, first I have to scale it up to have the same size as this. So that you have the right spread. And so the first thing I would do is I'm going to do some gamma times u. These are my standardized data. Start off with something, I standardize it, it becomes u, the z's become u. Then I scale it up, and then I add something. So the way I shift it to the new location is to first scale it up in place, add the origin, and then add something to move it to the new location. And that gives me the adjusted position. That make sense to everybody? Right. So what are all the things that we would have to estimate for this to work? We would have to determine what the gamma is and what the beta is. How much do you scale it up by, and how much do you shift it? Now this is easy, right? So I can redraw it like so. This is my normalization step. Z becomes u. I scale it up by gamma, add my shift. And now I've moved it to the new location, right? And this simple step of normalization and shifting destroys the simplicity of back propagation. Why is that? When I'm performing gradient, when I'm computing my derivatives, the way I did it, I had a loss which was the average of the divergences for the entire mini batch. And then when I computed the derivative of the loss, because of the additive nature of the divergence, of differentiation, the derivative of the loss with respect to any parameter simply became the average of the derivatives of the losses for the individual training instances with respect to that parameter. This was easy to do. And so I could just compute this derivative individually for every training instance. Now I can no longer do that. Why? Because when I've done this adjustment over here, this adjustment, the shift of z to u has used a mean and a variance. And the mean and the variance are functions of the entire mini batch. So if I want to write it properly, this is what it is, right? And so, which means this is the actual operation that's going on. There's a bunch of z's, all the z's for the entire mini batch. And every z influences the mean. Every z influences the variance. So if I perturb one z, the u for the other guys is going to change. And so this is, if I want to actually draw the picture here, this is what you'd get. You have the mean of the mini batch, you have the variance of the mini batch. This is the collection, this is the entire mini batch. Every instance in the mini batch is used to compute the mean. Every instance and the mean are used to compute the variance, and the mean and the variance are used to normalize every one of the u's when you perform this standardization, the first step of standardization. And this adds complexity to the derivatives. So, of course, when you're propagating backwards, this is easy. Propagating all the way till, say, this place is going to be easy, right? The adjusted location. That's just a standard backprop. Then going from here to here, I'm going to need to compute two derivatives. I have the z hat was, how did I write this? Gamma u plus beta, right? And when I'm going backwards, I would have the derivative of the loss with respect to z hat. So what is the derivative of the loss with respect to gamma for that instance? Come on, guys, this is easy. Yeah. So this is going to be the derivative of the loss with respect to, this is gamma. Gamma, right? Is going to be times u. And the derivative of the loss with respect to beta is simply going to be the derivative of the loss with respect to z hat. So we know how to compute the derivatives with respect to these parameters going back. Easy. Yes or no? Okay. So that we can compute. So I can compute if I'm, when I'm going back, if I got a z hat, I'd compute an activation on it. So back propagation will give me the derivative of the loss with respect to z hat, just propagate it past the activation. And then I can take a step back and compute the derivative of the loss with respect to the parameters of the shift, the beta and the gamma. And then finally, I must compute the derivative of the loss with respect to, what's the next thing I'd need? Z. To the u that goes in, right? And so what is the derivative of the loss with respect to u?
Gamma. LDC times gamma.
It's just going to be, I'm writing all over the board, pardon me, but the derivative of the loss with respect to u is going to be simply the derivative of the loss with respect to z hat times gamma. So that's easy, right? That was not complicated. So if you guys have not, are not awake yet, you're going to help me through the rest of this derivation, differentiation. And I'm going to pick on random people in the classroom and on Zoom, so you better have your eyes wide open. Okay? So that means I can compute my derivative of the loss with respect to the u's. And so over the mini batch, I have computed the derivative of the loss with respect to every one of the u's going back. What must I do next? What is the next derivative I must compute? The derivative with respect to all of the z's, okay? So is that going to be simple? Okay. Now let's look at what happens here. I know first. Okay, I'll answer it when I get back to the bottom, right? So, okay, let's answer these questions. What's your name? Tongwen. Okay, so what is the answer? Is the first statement in the first question true? Pardon me? The second one, all right. And Mary, since you shut yours, what about the second question? It's true, okay. So, and the first one, you got the first one wrong. In batch norm, the normalized U for any Z depends on all the Z's in the mini batch, right? It's not locally computed. And it's not that the Z's depend on all the other U's. Remember, the direction is going from Z to U over there, going left to right. So second, of course, the batch norm at any location is really a vector operation. You have a vector of terms going in and a vector of terms coming out. And so this is the challenge, right? So let's look at how the derivatives can be computed. Here is the complete set of dependencies. You have a bunch of U's going in. Together, all of these U's are you have a bunch of Z's going in. All of these Z's are used to compute the mean mu. Then again, all of the Z's and the mu are used to compute the sigma. And then when you find the normalized value U, you're subtracting the mean and dividing by the standard deviation. So this means that in order to compute any U, you're using the corresponding Z, but you're also using the mean and the variance. So this is the complete set of dependencies, the influences for this particular computation, right? So now, if I want to compute the derivative of the loss with respect to any Z, like so. Now, for say, the derivative of the loss with respect to Z1. This Z1 influences all of the U's, which means that if I want to compute the derivative of the loss with respect to Z1, I have to sum over all of the U's. So it's going to be the sum over all of the U's of the derivative of the loss with respect to U, which we've already computed, times the derivative of U with respect to Z. And so which is the term that we must compute now? Can somebody say it aloud? D, duj by dz. Can everybody say that aloud, please? Which derivative do you need to compute, the first term or the second? Okay, guys, please wake up. So this term is already computed. This is the one that we need to compute for every ij pair. And so you folks at the back, you're going to be helping me with this, right? Let me look at this. Let me look at the through line. So the through line is where ui, zi is used to compute the corresponding ui. So I and j are the same, right? So that is this term over here. So if I'm looking at the relationship of any ui to the corresponding zi, that relationship is given by this formula here. Ui is zi minus mean divided by the standard deviation. The plus epsilon is only to prevent division by 0, right? So let's look at all of the ways in which the dependency happens. First, you have the, what we are going to try, what does the derivative tell us? The derivative tells me how much does perturbing the zi change the ui. Now, perturbing the zi is going to change the ui through many different paths, right? So the first one is this one. So if I perturb zi, you're going to get a direct influence on ui. And so you have one component, which is the partial of u with respect to z through the direct path, right? So Yulin, can you give me another path? Over here, how perturbing ui could influence zi.
The other,
Which one? Can somebody else help her?
I think the first layer.
Is it UB?
Okay, so this is going to be through the mean. So what would that be?
dui by d mu v.
So that's du over d mu plus d mu over d sigma, right? Z. So you guys at the back, maybe I can catch this. Sungwon Wu, can you tell me if there's any other path from the input to the output? Sigma. So what would that be? Anyone want to help him? Yes?
It would be DI over D sigma
Fine.
squared. Times D sigma squared over DC.
Beautiful, right? That's all it is. So this is the complete set. Is there any other path left? No. So if you want to compute the derivative of ui with respect to zi, these are all the terms you want to compute. This is the nice thing about drawing these pictures. Once you draw the picture, everything becomes very obvious, right? And so can we compute these individual terms? Can somebody help me compute this first term? What is dui over dzi? Right, so what is this guy here? Is it 1? So, okay, now let me ask someone. June Kyung, what is dui over dzi? 1 over sigma? Yeah. So that's 1 over
Professor?
square root. Yeah,
Could you go back a slide for a second?
yes.
For the case where you're considering the derivative with respect to the variance, why isn't there a term for dub with respect to the variance? Like the
So
derivative of sigma variance divided by derivative of
we'll
the
get to that. We will get to that. We'll go through this one step at a time, right?
okay.
So the first step. So that's a good question, and we'll get to it. I promise you. So what was dui over dzi again? 1 over sigma. So that's everybody agree that this is true. This comes from the highlighted yellow equation, right? So let me write this here. Second term, what is du over d mu b? So can somebody help me? Himansh.
That would be
Come on, look at the equation. I know you're jumping, you know the answer. So, what is the answer?
it would be 1 divided by root of u squared plus eta.
Is it 1?
Minus 1.
Minus 1, right? So that's going to be just minus 1 over square root of sigma squared plus epsilon. So let me plug that in here. Easy. Right? So, what is the next term to compute?
I think you're the battery died on the microphone.
Oh, let me. I think there's one. While I'm getting this sorted out, guys, can you think of the other terms? Because I'm going to be asking. There's another one of microphone. I have spare. Thank you. Okay, guys, what is the next term to compute? Lehong.
It's like mu b over
So what is this one? What is that? What is d mu over dzi? 1 over b, right? Right. I have highlighted the equation very helpfully for you. Mu is 1 over b times the summation of all the zi's. Beautiful. I've dumped it here, right? So now, there's one more term. So this is the next term. What is this one here? Well, it's du over d sigma squared. What is it? Somebody, okay. Virginia, you answer this.
It's negative ci minus mu b over, I cannot do this in my head. 2, that's a half, so 2 times sigma squared.
That's just this guy here, right? So that comes from this. It's sigma squared raised to minus half. So u times, it's going to be z times, u is z times sigma squared raised to minus half. We'll skip the second term. So it's going to be minus half times u times sigma squared raised to minus 3 over 2. So Everybody agree with this? Yes or no? Right? Raise your hands if this is okay with you. Okay, thank you, right? So now that leaves us with this last ugly term, which somebody asked me about. And now if I look at the dependence of z of sigma squared with respect to z, there are two incoming edges again. So once again, you have to go through all the paths. Sigma squared has a direct connection to z, so the first term is the derivative of sigma squared with respect to z. And the second is the connection through mu, and so I have to consider the derivative of sigma squared with respect to mu times the derivative of mu with respect to z. Everybody see this, right? Okay, so what is the first term? What is d sigma squared over dzi? Anyone?
CI over mu, B over B.
So again, that comes from this formula here, this one. So what is d sigma squared over dzi?
2CI minus
ZI divided by B.
So it's going to be, this one is going to be 2 over b times z minus mu, right? Easy. That was so easy to plug in. And so that leaves me, let me put this here. Now let's look at this one. What is the derivative of sigma squared with respect to mu? So go back and look at the same equation again. That's the second equation, right? So this is going to be, 1 over b minus 2 sigma z minus mu. But now we have to sum over all the z's because, the sigma appears for every single z. And what is this term over here? Just without looking at this board, what is summation zi minus mu, where mu is the average of the zi's?
0.
What is that? What is the sum of all the terms after I've subtracted the mean?
0.
0, right? Because what am I doing? I'm finding the center of all of the data points and moving everything to that center. And if you want me to prove this, then I say mu equals, this is summation zi minus, so if there are b of these, minus b times mu. But what is summation zi? This is b times mu minus b times mu. So you have 0. Because z is, again, where did this come from? Because mu equals 1 over b summation I zi. So that gives me this guy here, and this comes here, so this cancel out and go to 0. Everybody with me? Right. So this goes to 0. I don't need to worry about the second term. And so here is this entire ugly derivative. Is this ugly? Or was it hard to get? How many of you still think this was difficult to derive? Raise your hands. Why? I mean, if you work through this one step at a time, there is nothing particularly complicated about this, right? We could just work our way through it and you get the answer.
Can I ask why could you sum the thing together rather than applying the quotient?
Can you
Could I ask why could you sum the last term rather than applying the quotient to the derivatives? Since it's a quotient, it's not like a direct sum or anything.
I'm not sure I fully understood the question. So if you're looking at this, are you speaking of this guy here?
I'm just thinking of the general equation. The last time we're dealing with the sigma b. I'm not sure why you can just directly sum the derivative rather than having to apply the quotient to, because you're essentially having a function based on z over another function based on z.
Right. And so you could, yeah, but then again, the derivatives are going to have all of these terms, whether you like it or not.
Yeah.
So we're just deriving all of the terms. I'm not sure. Let's take this on Piazza because this might end up taking more time than we have. I'm sure it's a question everybody will deal with this on Piazza, right? Because the calculus of derivatives is a painful thing. We get intimidated. But then when you actually work these things out, it's so trivial that these days you can just say, write an autodiff which computes all your derivatives. So here's where we are. So this was only for the derivative for the through line. the straight line, zi going to ui. You would need to compute the same thing for the cross lines, right? Like z1 going to u2. What is the derivative of u2 with respect to z1? So in this case, what are the terms going to be? Anybody?
With respect to mu b and
So this is going to, Theo, can you tell me?
I think it's just the second two from the previous.
Yes, it's going to be u with respect to mu, mu with respect to z, and then u with respect to sigma squared and sigma squared with respect to z, right? And I won't work through this. I'm sure you guys can do this all by yourself now because we know how to do this. And I'll just give you the answer. This is similar to the equation for I equals j without the through term, and the answer is going to be this, right? So far so good. We know how to derive the formula. And so the derivative of uj with respect to zi is going to be this first term if j equals I, and the second one if j is not equal to I, okay? And let's plug all of this into our loss function. The derivative of the loss with respect to any z is going to be the sum over any zi is going to be the sum over all the u's of the derivative of the loss with respect to that u times the derivative of the u with respect to the target z. And if I write this out, up there is the equation for the derivative. And so let me plug all of this guy here into my derivative equation. I'm not going to work this out. You're going to have to believe me because it's fairly straightforward. And so this is what the derivative of the loss with respect to any zi looks like. Now it's a complicated and ugly looking equation, but it tells us gives us some very interesting information. Where did I keep my chalk? Right there on the board. Okay. So let's consider a case where my mini batch consists of the same training instance repeated over and over and over again, right? So if that happens, then I should be able to write simply the derivative of the loss with respect to any ui is simply going to be the derivative of the loss with respect to u, because all the training instances are identical, correct? So that first term simply becomes d loss over du times 1 over square root of sigma b squared. I'm too lazy to write the epsilon, okay? What does the second term become? What does the second term become? Anybody want to help me?
the b in the denominator goes away.
The second term is going to be 1 over b times 1 over square root of sigma b squared times I equals 1 to b, simply d loss over du, because all of the ui's are identical, right? And so what is this one here? I'm just summing this b times, so this is the same as b. Multiplying this by b, right? And so these go away. And so is the second time now any different from the first term? So what will happen to the first two terms? They will cancel out, right? What about the third term? What does the third term look like? Over here. So for the third term again, I can write summation. There's a whole bunch of blah outside, and then there's a summation d loss over duj zj minus mu, right? But d loss over duj is the same for all the j's. So this comes out. So this is d loss over du times summation zj minus mu, right? And there's some additional stuff outside. What is this guy here? 0. Right? So what does the third term become? 0. So what happens to this derivative if the entire mini batch is identical? What happens to the derivative? Guys, can everybody say this aloud? What is the final value of the derivative if the mini batch only has the same instance repeated over and over?
0.
Thank you, right? So this is one of the issues with this kind of batch normalization. the implicit assumption in batch normalization is that there's diversity in the mini batch. The moment the diversity in the mini batch disappears, firstly, not only do we get these huge covariate shifts, when you're passing the derivatives back through the mini batch, they can just disappear and go to zero. So it's very important for the mini batch to actually have diversity, and then when you do, then the derivative of the loss with respect to each of the zi's, where the zi's are the z's for the mini batch, can be computed straightforward. Yes?
Is this really like happens that all the U's become zero in the
I'm sorry, can you say that up?
Is it really like practical and happening that all the U's become?
It's a random sampling that you're performing. There's no guarantee that it won't happen, right? So it's unlikely, but these are things that you would have to watch out for. And to answer your question previously, this was the same thing that someone else had asked. Why do we need to go from U to Z? Why do you need to scale and shift? The assumption is that at that location in the network, the natural distribution of the variables lies somewhere. We just don't know where, but it's unlikely to be at zero. So we're trying to find that.
Gamma, sorry. Mu and gamma become like two new variables.
To move it there, yeah. Okay, so this is for people on Zoom. I'm giving you guys 60 seconds. That was great. Okay, that's easy. Someone on Zoom, can you answer the question? Zoom? Anybody on Zoom?
True.
True.
Thank you. Right? Batch norm effectively blocks backprop and prevents gradient computation if all the instances in the mini batch are identical or very similar. True. Yes?
Why very similar?
So very similar is that basically look at all of these terms. These terms, if they're all very similar, this is going to go almost to zero. These guys will almost cancel out. So the derivative is going to become small. So if they're identical, it becomes identical zero equal to zero. But the less diverse they are, the smaller the derivative is going to be. Okay, and now, so this is so far so good. Yeah.
How do we initialize gamma and B?
So 1 and 0 would be perfectly, yeah. Assume that, you let it move, right? So you've got 1 and 0 would be assuming that it stays right there, and then you let the training figure out where it goes.
Is it too expensive to take the average over all the mini batches and then be like, okay,
The first time you're training, you're not going to know where things are anyhow, right?
okay.
So it will be noisy, but yes.
If it prevents backpropagation, then how do you backprop to previously?
So the point is you want to make sure that your mini batch has diversity. That way it will not prevent backpropagation. So this is about the design of the mini batch itself, right? And so here's the other thing. This was during training, but when you're performing inference, there is, you have no idea, you're not working with mini batches, you're working with one instance at a time. So what is the mean? Whereas the mini batch, the batch norm has these two parameters, the mean and the variance. Where do the mean and the variance come from? So for this, since you're working with one instance at a time, there is no notion of a mean of a batch or a variance of a batch. And so this has to be sort of guessed. And so typically what you would do is once the network is fully trained, you would pass all of your data through the network. And each mini batch is going to have its own variance and its own mean. And so the overall mean that you'd compute, you come up with a hypothetical mean and a hypothetical variance. Had this instance been part of a mini batch, what would the mean have been? Had this been part of a mini batch, what would the corresponding variance have been? And so that is simply computed as the average mean and the average variance of all of the mini batches in your training data once the model has converged. Now, you don't actually do this, quite in this manner. You'd maintain running estimates of the means and the variances. And how you do this can greatly affect how well your model works. And in fact, in PyTorch, we've run into various issues where if you just set the flag wrong, then just using batch norm will kill your inference, although things look very beautiful in training. So you must be careful. And she would be the person to tell you all about it because she has suffered greatly. Yes.
So if you are using the mean and standard deviation from the training set, and let's say if in the test set our distribution is slightly different, so wouldn't it cause some problems?
It would. It certainly would, right? So this is the best guess that you're taking. That's about it. And one of the so for in PyTorch, for instance, if I pass a batch of samples through the network in training mode and in inference mode, in training mode, it's going to use the mini batch mean and the mini batch variance to compute the parameters and the loss. And inference mode is going to use this running estimate. And so here is one instance where, in a standard network, but it doesn't really matter whether you're working in training mode or inference mode, the output is going to be the same. But once you introduce batch norm, that goes away. And so nasty things can happen. Yeah.
So then mu and beta would be a shared variable between all the mini batches, right?
The gamma and the beta are, yeah.
Professor, can you repeat what inference mode was?
So the inference mode is where you're actually, when you're performing, when you're using it to actually perform classification, then the mu and variance that you would use are the ones that are currently on the slide, the ones that you aggregated as running estimates during training. Whereas in training mode, you would actually use the mean and variance of the mini batch itself. So in inference mode, you're assuming that you don't have access to anything of this kind, that every instance is an instance unto itself. And so you have to use guesses for the means and the variances, and that causes problems. There was another question?
Yeah, I had one, but the very bottom line answered it.
Okay. All right. So, and batch norm can be applied, to some layers or some selected neurons. The whole point of batch norm is that it's not enough to apply it once. Even after you standardize things, there's still some fluctuation. And then as you go through the network, those things can get magnified. So you have to keep doing it again and again, right? Anecdotal evidence is that batch norm eliminates the need for dropout. Now, there are large rational reasons for this. I haven't yet discussed dropout, but we can discuss this on Piazza if you're interested. And to get the maximum benefit from batch norm, it turns out that we need larger learning rates because you're normalizing everything. The derivatives behave more nicely. So you can increase the learning rate and have things converge faster. And you need randomization of the data for this thing to work. As we saw, if the batches look very similar, the gradients can vanish. And here's the first paper on batch normalization by Eof and Zagadi. And they show how once they use batch norm, you get to better solutions after just a few steps than you would after very, very, very many steps without batch norm. So it really helps. And you're going to be using this in your homeworks, right? So to add to our list of lessons, covariate shift between training and test can cause problems and can be handled by batch normalization. There's another problem, which has to do with the fact that I've been lying to you. So when I say I've been lying to you, this is, I've been drawing pictures like this, right? Where I say you have a bunch of training points, and the training points, if I just fit the data on the training points, this should be enough. I can hopefully estimate my function. And so all we did was try to minimize the total error on the training points. L2 or KL divergence. There's nothing stopping the function from learning something of this kind, right? It could just fit the training points perfectly well, and everywhere else it can be completely gobbledygook. So how do you prevent something of this kind from happening? You need additional smoothing constraints that will fill in the missing regions acceptably. And how can you do that? To see this, let's take a look at this very simple problem where I have a one-dimensional input, I have a fairly complicated network, and the outputs are either 0 or 1. Now, in this kind of a situation, we saw that what you really want to estimate is something that looks like a sigmoid. But there's nothing. You remember that our neural network is a universal approximator. There's nothing stopping the network from learning this function here. Which of the two would you prefer, the purple one or the blue? Right? The purple is kind of, I mean, maybe there are situations where the purple makes more sense, but the reality of it, that's what you would call a terrible overfit, right? What you really want is the statistical estimate that you get from the blue curve. So why is this function able to compute the purple curve? That's because the network itself, every neuron in the network is able to compute functions with those extremely steep slopes. And to give you an idea, if I were just using a sigmoid smoothly goes from 0 to 1. But then the sigmoid has this parameter w, and as I increase w, the sigmoid gets steeper and steeper and steeper. And the limit, when w becomes infinity, the sigmoid is just going to become a step function, right? So if you want to prevent the sigmoid, this is going to be true of every activation function you use. If the slope is very large, it's going to eventually just give you a discontinuous function. And so that is why the network can learn something ugly like this, right? So if you want to prevent this from happening, what would you do? You want to ensure that the weights don't get too large. And so you impose a constraint. Steep changes that enable overfitted responses are facilitated by neurons with large W. So you want to constrain the W to be low. And this forces slower perceptrons and smoother output response. So how can you do that? Your standard loss is simply going to be the average of the divergences for all the training instances. Now you add a second term. You say that it's not sufficient to just minimize my loss, also ensure that the squared norm of all of my weights is as small as it can possibly be, while also minimizing the loss. This makes the weight smaller. It makes the function smoother and slower. And so this is less likely to give you the ugly kind of overfit that we just saw. And this doesn't really, and lambda over here is basically a parameter that determines how important it is for the weights to be small. This doesn't really change our update rules very much. So Lei Hong, you want to go and wash your face? So how does it change our learning rules? This was the old loss. That's just this. The new loss also has the second term. When I compute the derivative is the average derivative of the divergences plus, and now because I have half lambda times the squared norm of W, what is the derivative of the squared norm of W? It's just W itself. So it's lambda, and because I have a half, the 2 cancels out. You just get lambda times W. And so when I adjust my, so the derivative of the modified loss is the traditional derivative computed using backprop plus lambda times the weight parameter itself. So if I take this step, W equals W minus eta times this guy, it's going to be W, this lambda over here. If I write it, it might be simpler, but then I have to find my chalk. So, yeah. We had W is W minus eta times the derivative of the loss, which was W minus eta times I'm calling this the backprop derivative that you got when you perform backprop minus plus lambda times W, right? Because this was what you got from the second term, which said you have to minimize the length of W. And if I just put these together, this is simply 1 minus lambda times W minus eta times your backprop derivative. Or this eta would be outside, but I can, whatever. So you get the idea, right? So what happened over here? If I simply multiply my current W by a scalar, I shrink it, and then I add my derivatives, I get the natural outcome that it not only learns the parameter, it also ensures that the parameter is as small as it can possibly be. You encountered this in your homework. What did we call it? We call this something, right? What do we call it?
Regularization.
Not just regularization. We had weight decay. We call this weight decay, right? because the 1 minus lambda term shrinks the weights before you add the corrections. Yeah.
Was that intentional, that the way that we penalize our loss function leads to this?
Yes. Yeah. Questions? Okay. So this was just a standard modification to your backprop rule. We just got 1 minus lambda times W times the correction, okay? And the other way you can actually get smoothness is by just adding many, many layers. Typically, your weights are going to limit the slope of the function. So the more layers you have, the smoother the function is going to be. So for the same number of parameters, having a larger number of layers is going to give you a better estimate. We have a little example here where we were trying to compute functions for these two different decision boundaries. And if I do this carelessly, the decision boundaries that you actually learn are the ones to the right. These are with the optimal, with networks which have the capacity to learn these functions. They just give you this garbage. Whereas, if I do things differently, here are a few different decision boundaries I'm trying to learn. In every case, I have 660 neurons. So in the first one, if I model this function using 3 layers of 220 neurons, this is the boundary you get. This is with 4 layers of 15 neurons. This is 6 layers of 110 neurons and 11 layers of 60 neurons. And you can see that as you keep the same number of neurons, as you make it deeper, it keeps getting better and better estimates of the actual decision boundary. That's because if you redistribute the parameters for the network to be deep rather than wide, then the depth by itself introduces a regularization that makes sure that you learn things properly, provided you can learn.
Professor, why does the depth introduce regularization?
So we'll get to this in a few lectures when we are talking about gradient decay and such like. So hold on to this question. Either post this on Piazza or remind me in a few lectures, okay?
Professor, question.
Yeah.
With the example you gave on weight decay, does it mean that when you're not using an activation like sigmoid, weight decay may not really be necessary? Does it mean that, or does it apply to all?
So this is going to apply to pretty much any activation, because if you increase the weight arbitrarily, the functions can become very steep, and that's what you're trying to prevent. Okay. So now there have been other techniques that have been proposed to improve the smoothness. L1 regularization of network activations, regularization with added noise. But I'm going to spend the last 9 minutes talking about the next most influential procedure, which is dropout. Now, before we do that, before neural networks became all the rage, a lot of research went on to how you could train many machine learning models and ensemble them to get a better model. And one of the most popular methods was called bagging. It has provable properties. And the way you would perform bagging is that you would draw random samples from your training data. And from each random sample, you train a different model. And then eventually, you have a collection of models. And each model would give you some kind of an outcome, yes or no, whatever it is. And then you vote it across all of the models that you trained. And this was probably going to be better than simply throwing all the data into one big bag and training the model, provided you did this right. So bagging was very, very popular. So hold on to this idea and just believe me that this works. And then let's go on to this notion of dropout, right? So dropout, well, during training, in your standard training, you have a network of this kind. For each input at each iteration, in a standard network, all the data is going to start at the beginning and go through to the end. If you use dropout, for each input at each iteration, you're going to turn off these neurons with some probability. So maybe for the first neuron, you turned off this set, which are marked in black. So the actual computation is only done with the rest of these neurons. And then the next input came in, and then so you're basically flipping a coin at every neuron. And the coin has a probability of heads alpha. You keep the neuron on if it turns up heads, otherwise you switch it off. So each input is going to see a different network because different neurons are switched off for each input. And moreover, if you went through the training data in epochs, the set of neurons that were switched off when a specific particular input went through the network could be very different than the set of neurons that were switched off the next time it went through the network. And this is shown to really, really improve performance. So what really is happening over here? The pattern of drop nodes changes for each input in every pass through the net. And when you perform back propagation, you're only going to be computing gradients over the net that remains when things are switched off. So now, what is the interpretation of this? We've all employed dropout in our homework. What really is happening? Now, if you think of a network with these many neurons, then I can think of this in terms of bagging, right? I can build many different models. So I could build one model switching this guy off. Just peel this off the network. That's one model. Peel this off the network. That's a different model, right? So how many different networks then can I compose just by switching things off on this network? If I have n neurons, 2 raised to n, right? So because each neuron could be switched on or off. And so effectively, what we are doing is treating our network with n neurons as a collection of 2 raised to n independent networks with shared parameters. And for each input, you're randomly sampling one of these networks and passing the input through the network. So in the process, you're training this entire set of 2 raised to n networks all at once over using your inputs. And so this is basically the same as bagging, right? You're training a collection of classifiers, and each of them is basically seeing a different set of inputs. And then when you perform inference, you're going to perform inference using the collection of classifiers. What's the problem with trying to do this naively? You're saying something? 2 raised to n networks. You can't possibly evaluate your input using all 2 raised to n networks. So you're going to need an approximation, right? So this is one. There's also a second interpretation to this, why this works. If you just naively train your network, there's absolutely nothing stopping your network from one layer of your network from simply being a pass-through. So for example, this layer might just learn to simply copy this input here, effectively removing the layer from the network. And so you might be thinking you are training a 16-layer network, but you're only training 14 because 2 of them just became pass-throughs. But then if you have dropout, because you keep occasionally switching off these neurons, the neurons are forced to look at an aggregate of information. And so you're forcing them to learn richer, denser patterns and ensuring that they just don't simply, some layers don't simply become pass-throughs, right? So this is the reason to be doing this. Now, do you mind switching your phone off? You know, if you're looking at the phone, go outside and do it. Can you turn the phone upside down, please? You, yeah. Turn it upside down. Thank you. Yes. Yeah.
When you're doing mini batches, do you drop the same nodes for the whole batch?
No. Every instance is going to be very different, right? So here's how you'd actually implement it. I may go over a couple of minutes. Bear with me, guys. So as you're going forward, you estimate a mask, where the mask determines which neurons you're switching off and on. And then when you go performing back propagation, you use the same mask going back. Right? So just look through the slides. I'm in a bit of a rush because the next lecturer has an exam. But one final thing, when I'm testing with dropout, here's what we wanted to do. We wanted to take a collection of networks and we wanted to get the average output across the networks. So we want to take the expected output over the entire network, which means you'd have to pass the input through every network in the collection, which is going to be infeasible. So we use a crappy approximation. We say the expectation of the network, where the network itself is a function of neurons, can be written as the network of the expectations of the neurons. And so once I write it this way, for inference, what happens is that every single instant, all I'm doing is that I'm replacing each neuron by the expected output using dropout. And what is the expected output using dropout? Each neuron is actually now a Bernoulli variable, right? The output of the neuron was multiplied by some variable d, which became 1 with probability alpha and 0 with probability 1 minus alpha. So the expected value is simply alpha times the output of the actual output of the network. And so during inference, all you'd need to do is to multiply all the outputs by alpha, and you're done. Now, there are different ways of doing this. You can pre-multiply all the weights by alpha and not multiply the activations by alpha during inference. Or during training, you can use alpha inverse times the activation during training, so that you can just use the network as is during inference, and all of them are equivalent. So I have some pseudocode for this and some typical results. Dropout can really help, except it has this issue that it can conflict with batch now. So there are various variants for dropout, zone out, drop connect, shake out, white out, what have you, but they're all basically built on the same kind of principle. So the story so far, adding the final 2 lines, data under specification can result in overfitted models and must be handled by regularization and more constrained architectures. And dropout is a stochastic erasure method that sometimes forces the network to learn more robust models. There are other things, heuristics like early stopping. You test the data network on some validation data, and when the performance on the validation data begins to get worse, you stop training. Another thing that happens is that when you compute derivatives, for some instances, the derivatives can become too large. So we like to clip it to prevent this from happening. Otherwise, that one instance is going to cause your network to blow up. If you have performed your training and you track your losses, every now and then you'll see the loss boom. That's because there are some instances in that mini batch with ugly derivatives. Clipping it will help. We can create fake data by distorting our data, various other techniques. They're all on the slides, most of them anyway. I'll stop right here. And in the next week, we'll begin talking about convolutional neural networks. Please take any questions to Piazza. Thank you.